Alright, so this is going to be episode 1 of my new series that I'm calling E&M 1, or Electricity and Magnetism 1, where we're going to go over modeling of static configurations in electricity and magnetism. And in this first episode, we're going to be briefly introducing Coulomb's Law and the electric field. By no means is this going to be the only video where we go over the Coulomb's Law or electric field. So if you have any questions at all, feel free to leave them in the comment section down below. And in episode 2, we're going to be taking all of the material that I'm introducing here and applying it to an example. Let's get started. Okay, so if you remember back to your introductory physics days, you probably remember being taught Coulomb's law some kind of way like this. Coulomb's law, or electric force, is equal to kq on r squared, but there's something wrong with this right now. There's no directionality. Now, in an introductory physics course, you were probably taught to look and inspect the configuration, determine the direction of this force, and then add it on to the magnitude that you were going to end up finding in a problem. But since you hopefully have a good grasp of vector calculus, we have a new way of defining it. If we expand out our constant, we get 1 on 4 pi epsilon naught qq on the magnitude squared of what we're going to call the curly r vector in the curly r, and this is all going to be in the curly r hat direction. Alright, now just to define a few things, we're going to define big Q as our source charge, little q as our test charge, and curly r vector is r vector minus r prime vector, where r vector is going to formally be defined as the distance between a source charge and a point charge. Let's quickly hop over to the whiteboard for a quick and easy example. Okay, so here you can see we have the following example where we have a source charge located at minus x on the x-axis, and then our test charge at plus x on the x-axis, and we want to establish our curly r vector for this situation. Our curly r vector is going to be the distance from our source charge to our test charge. Remember, so this distance right here is our curly r vector, okay? It's our curly r vector. And so here, our curly r vector is going to equal r minus r prime, where r is, of course, the distance from the origin to the test charge, and r prime is distance from origin to the source charge. Okay, so let's write that out. Our test charge is located at x0, 0. Alright, if we're thinking about this in 3 dimensions. And then we're going to do minus negative x0, 0. Okay, and then we just simply go through and do our vector subtraction to get 2x, 0, 0. Okay. Really simple, really easy way to go about doing this, and really this entire thing just ends up equaling 2x x hat. And the reason why I write it this way is because it's really easy to see that curly r hat is x hat, okay, as our directionality. Okay, so now that we've gone over brief little introduction to the curly r vector, I hope that from introductory physics you understand, or at least remember, that an electric force comes about whenever we put a test charge into an electric field, okay? And so we could really just write out our force equation just like you see right here. Okay, and if we just simply take out our test charge, that should give us our equation for electric field, and lo and behold, it does. That's our understanding of electric field as we know it. Okay, and really, this only works though for a singular source charge. Okay, and so when we add more source charges, we simply just have to sum them all together. Now, hopefully you can see that we're leading up to lines of charge, or areas of charge, or volumes of charge, where this sum is quickly going to turn into an integral, but that's going to be for later episodes. In episode 2, as I mentioned before, we're going to be applying this formula and actually modeling the electric field of a certain configuration, so tune into that. But otherwise, again, if you have any questions, leave them in the comment section down below, and I'll do my best to answer them as best as I can and as quickly as I can. But otherwise, thank you very much for watching.